Welcome to the wonderful world of prosthetics. Have you or someone you known ever lost a limb? Can you imagine the lack of mobility and the physical and psychological pain they must go through each and every day? Research is constantly being done to improve the lifestyle and ease the pain. But with every good technology, there are downfalls. Today you'll be learning about the research that touches on these downfalls and leads to a better world of prosthetics. Well, hello there. Tonight on my show, we will be joined by Kate and Tassie, who are biomedical experts on porous polymers. Welcome, ladies.
Hello, Andrew. Thank you for having us.
Yes, thank you. We're really excited to talk about our research.
That's great, interesting. How are prosthetics related to polymers?
Well, since the problem with prosthetics, especially with the physically active, is discomfort at the attachment site, the polymer alleviates some of this discomfort. So through our research, we're determining the effect of polymer processing on the prosthetic attachment site.
So what exactly do you mean by processing? Can you please elaborate?
Yeah, since the human body doesn't like the idea of interacting with a random foreign material, a polymer that is compatible with the human body is necessary for optimum prosthetic use. Polymer structure can be processed to include pores. A porous polymer has the ability to better agree with the biomaterials of the body.
Of the new joint. After some weeks, the pores of the prosthetics start to get filled with the new bone, and the bone tissue would start to grow around the prosthetic. The growth process takes between months and a year, but in the long run, it's very beneficial for comfort at the attachment site.
So how exactly do you make a porous polymer?
Well, porous polymers are made by the process called phase separation by thermal induction. So the solvent is changing the polymer properties, causing phase separation. Thermally induced phase separation is the most versatile and simplest preparation technique there is. With it, we can control the size and the shape of pores within the polymer. The solvent that is added to the polymer is removed after the cast solution is cooled through solvent extraction, leaving behind a microporous structure of desired characteristics.
And this actually lowers the energy of the polymer, and the polymer-rich portion resolidifies while the polymer lean portion turns into pores.
What are the benefits to having a porous polymer?
Well, first, in order to understand that, we have to talk about the three main parts to any prosthetic. So the first is the pylon, which is the internal frame of the prosthetic. Then is the socket, which is the part that attaches to the residual limb. Finally, there's the suspension system, which keeps the prosthetic attached to the limb stump. Now, in terms of wear and tear, prosthetics generally last only 3 years, because the human body is an ever-changing mechanism.
And therefore, the prosthetic will have to be modified or replaced at some time. The fact that the prosthetic does not change over time, whereas the residual limb does, causes the wear and tear, and since they're not perfectly fit to each other, the friction that occurs between the prosthetic and the limb wears the prosthetic down. And the porous polymers that would be covering the part where it's attached will help mitigate that, since although the polyethylene is strong, it'll also be malleable in that it can fit itself to the limb. And the socket, after a few months, will at this point be mostly bone tissue wrapped around the limb, and the bone marrow and minerals in the pores of the polymer will also help, and the body will acclimate to the polymer, making for a more comfortable and durable prosthetic.
Interesting. How do you implement a porous polymer?
Well, the porous polymer is essentially a type of cover or film that goes over the joint part of the prosthetic. The pylon-based layer of the prosthetic would be made of titanium and other strong materials, as usual. With physically active people, there's a lot of friction between the bone and the prosthetic. The friction can cause bone fracture at the attachment site, and this can be really painful and cause serious damage to living material around the joint. So the porous polymer would allow the device to be integrated with the tissues of the body, and therefore decrease the rough interaction and friction between the bone and the device.
How does the structure of a polymer surface play a role in implementation?
Well, We are actually in the process of researching the optimal size of the pores in the polymer coating. Currently, we see that bigger pores allow the device to be more integrated with the body, but they don't provide as much of the structural support that's necessary. But on the other hand, smaller pores do the exact opposite and do not integrate as well, but provide more structural support. So our data helps show that increasing the size of the pores decreases the tensile strength of the polymer, and finding the right size of the pores is definitely going to be the key into making this new technology the best that it can.
Also, polymers are highly dependent on the molecular weight of the polymer. So increasing the molecular weight of polymer coating would increase the strength. This helps show that smaller pores lead to higher strength since pores decrease the bulk molecular weight. We discovered that optimal strength can be achieved by combining two porous polymer structures, one with high bulk molecular weight, and then for smaller pores, and one with low bulk molecular weight with bigger pores. This creates a hybrid polymer that utilizes both porosity and strength.
With all this work being done, have you acquired any difficulties in your research?
Yes, actually. We have come across some material constraints. The structural properties of polymers have proved to be a speed bump in our research. Polymers are viscoelastic by nature, and this means that during evaluation, we need to make sure that we are not putting the material under too much strain. Polymers generally become stiffer under extensive strain, which could hinder accurate tests. And also, polymers, especially polyethylene, are prone to biodegradation when implemented in the human body. And the body is very hostile to made-man parts, and polymers will want to deteriorate as soon as they start interacting with the fluids and the tissues of the joint area. The deterioration affects the cross-linking of the chains and the side groups of the chains, and undesirable breaking of the covalent bonds in the cross-links can occur. This would ultimately break down the coating, and we would be back to the original problem. To make the polymer coating less susceptible to this degradation, vulcanization can be implemented to increase the percentage of cross-linking in the actual polymer. Vulcanization is a process that changes the properties of the polymer by heating the polymer with another material to cross-link the hydrocarbon polymer chains with the new material.
So where do we go from here?
Well, clearly, as you've seen, porous polymers are not perfect. There are limitations in the material, both structurally and in processing. So our material goal is to find the right size of the pores for coating, as well as figure out a way to process the material so that it will last for a long time in the body. Our ultimate goal is durability and improvement in the prosthetics. So unfortunately, no man-made material can fit seamlessly within the biomaterials of the human body, but hopefully through our research, we'll be able to get as close as we can.
Well, thank you very much, Kate and Tassie, for spending your time with us here today.
Thanks, Andrew.
Thanks.
This topic is very important to increase the durability of current prosthetics and to increase the comfort of amputees today. During this video, we hope that you learned a little bit more about the structure, the properties, and the processing that goes into polymers, which there is a lot of research going on right now to make better. So, thanks for tuning in. See you next time.